Right, let's start. Okay, so last time we studied about echelon form and the reduced echelon form and their conditions or requirements, right? And basically, if you follow the first step of a Gaussian elimination, and then the output of it is echelon form, right? And there were three conditions of this echelon form, right? And then once we complete the second half of this Gaussian elimination, then you obtain the reduced echelon form, and it had two additional conditions. So, for example, if we find those two pivots, or what was the pivot? If you remember it, and then pivot is defined as a leading entry or the first non-zero entry of a row, right? But that matrix should be in the echelon form. Okay, so the leading entry of an echelon form is called a pivot. Okay, so in this case, if we review those three conditions of a reduced echelon form, and then these kind of completely zero rows should be stacked in the bottom part, right? And then all the other non-zero rows should be above the zero rows. And then another condition is, once you found this leading entry or pivot in the echelon form, and then all the lower part in that corresponding column should be zero, right? And then the last condition was so if you pick up if you choose any of our pivot or leading entry in our echelon form, and then it is placed in the second row, right? And then we look at the upper rows, all the upper rows, and then we look for their leading entry or pivots, right? And then look for or check their column indices of the upper rows pivots, right? And then their column indices should be all on the left of this pivot, or this column index is 2, and so this is one of the pivots in the upper row, and then it's the column index is 1, right? So definitely 1 is on the left of the 2, or the second column. Okay, and then we discussed about in some cases. I mean, the question was whether there is any cases that satisfies only one of these conditions but not the other. So I mean, so once we found like this kind of condition, so in terms of the pivot locations, it should be on the upper left part, right? So I'm not sure if if that is satisfied, and then all of them should be 0. I mean, this condition, I think that is automatically satisfied, but not the other way around. For example, suppose we have a pivot like this. Okay, and then suppose we have all zeros and all zeros and all zeros, right? So in this case, for each pivot, and then all the lower entries in the corresponding column is all still 0, but that doesn't satisfy the echelon form, right? Because for this case, if we look at the upper row, this guy is not satisfying because it's not on the left side of this guy. Okay. Okay, what was so that was the three conditions of an echelon form, but in order to be reduced echelon form, there is two additional conditions or requirements that we need to satisfy, right? And so what was that? So the first one is all the pivots should be 1, right? So pivot is basically the first non-zero entry or leading entry of that corresponding row, but that value itself should be always 1 for every pivot or each pivot, right? And also, in the case of echelon form, given a particular pivot, 0 should be placed on the lower part, right? So that was the condition of an echelon form. But in the case of reduced echelon form, we now also look at the upper part, upper entries, right, in the corresponding column. All of them should be 0, which means for a particular pivot, for each pivot in the corresponding column, that pivot is the only non-zero entry. So the upper or lower will all be 0, right? So that is the condition of our reduced echelon form. Okay, then I mean, I'm just we are just reviewing what we already studied last time. So if you already understand it well, and then it might be boring, but it's so important. So I'm gonna just spend a little bit time on reviewing this. And so what we studied based on this echelon or reduced echelon form, I mean, we were able to study how to find or determine how many solutions we have in a given linear system, right? So first of all, we go through the first phase, and then we look at or we check whether we have this kind of column, or if we see the pivots in the last column, okay, so that's when we obtain the impossible kind of equation, which means 0 times x1 and 0 times x2 and so on is non-zero, right? That's what it means by having the pivot on the rightmost column, right? So that's when we have no solution at all, right? And then in that case, you don't actually need to finish the second step of this Gaussian elimination, because we can just conclude that we have no solution. So there is no point, no need to just make it reduced as a reduced echelon form and obtain the parametric description. So we don't need to do so because we have no solution at all. Even if we may have a free variable, right? Yeah. So, but if we don't find such a column, such a row, and then that's when we have at least one solution, right? And in that case, we can either have a unique or infinitely many solutions. So that depends on whether we have a free variable or not, right? And so the free variable is the variable that correspond to those columns that don't have a pivot, where the pivot does not exist, right? But for those columns that have a pivot in the corresponding column, and then those are called a basic variable, right? So once we obtained this reduced echelon form, and then as we see, these pink ones are pivot columns, or the columns containing pivots, and those are corresponding to basic variable. And this guy, which doesn't have any pivot, and that is corresponding to basic variable. And then once we obtain this reduced echelon form, and then we just convert it to this just the equation form, right? And then we leave all the basic variables on the left hand side, such as an x1 and x2, and then but we move all the free variables to the right hand side. Okay, so that way let's see, we obtain x1 is equal to 5x3 plus 1, and x2 is equal to so I already wrote it here, right? And then what about the x3? X3 is just a free variable, or that is the one that we can freely set as an any value, right? Okay, so that was a brief review of what we learned last time. Okay, and then now let me discuss a little bit on the uniqueness of our echelon form or reduced echelon form of a given matrix. So I'm not gonna prove it, but I'm gonna just tell you that given a particular linear system or augmented matrix, and then suppose we perform the first step of a Gaussian elimination and then obtain reduced echelon form. Echelon form, right? But yeah, depending on which person performs this operation. I mean, I suppose I did my own Gaussian elimination, and then some other student also did his or her own Gaussian elimination until the first phase, and then the result may be different, but still they may be they are still valid echelon form. Okay, so for example, let's see. Okay, so we know this is an echelon form because we see pivots, right? And then I also mentioned about this reversed kind of staircase shape, right? Or something like this. So inside of this polygon, we can have non-zero, but outside of it, it should be all zero. So this is an echelon form, right? But what about this? So somehow you obtained maybe 4 and -8 and 8 and -28. So is it still an echelon form? Yes, it is, right? Because it's satisfying all the three conditions of an echelon form, right? So given a particular matrix, the echelon form, echelon form is not unique, right? But what about the reduced echelon form? So even though, even if I obtained this echelon form, but some other student obtained some different echelon form, but once we perform the second phase for each person, and then the reduced echelon form will be exactly the same. Or in other words, reduced echelon form is unique given a particular matrix. Okay, again, echelon form may not be unique, but reduced echelon form of a given matrix is always uniquely determined. Okay. So what's the benefit of it? The benefit is, this kind of parametric description of our solution will always be the same. Okay, once we did the Gaussian elimination, and then if this one was formed based on reduced echelon form, and then because the reduced echelon form is always unique given a particular linear system, and so this parametric description of our solution will always be the same. Okay, any questions so far? Okay, then let's move to the next chapter about this vector equation. So in a linear algebra, the main things that we study, or main objects or entities that we deal with, is not just a scalar, but mainly like a vector and the matrices. Okay, so those are the main ingredients or the main objects or entities that we have to study. So now, we study about the vectors. Okay, so vector is basically a one-dimensional array of numbers, right? Again, one-dimensional array of numbers. But I think I mentioned about the two possibilities of having a vector given a matrix, for example, 1, 2, 3, 4, 5, 6, and then we can define this row vectors, right? And also we can define these column vectors, right? So in this case, this is just a convention, or just to avoid any trivial confusion, we just assume that all the vectors that we handle, or we think of, is column vector. Okay, this is just a just convention, which doesn't have any kind of right or wrong kind of notion. Okay, so we handle this column vector, and suppose that column vector is called a W, and W is in this example two-dimensional vector, right? And in terms of the notation, notation. So we see boldface letter here, right? So throughout our class, or in all the materials that we use, this lowercase but bold-faced letters indicate vectors. Okay, and then this kind of italic or just a mathematical kind of a notation written in a lowercase with an italicized font. So that is corresponding to scalar. Okay, just a plain font, right? So these are scalar, and their collection is a vector, right? And also, what is the length of an array in this case? The length of an array is 2 because this vector simply have 2 elements, right? And so we represent it as R2, or over here, this guy, this weird looking R. Okay, so that is a little bit bold-faced capital letter, right? So that is a set of all the numbers, but R indicates the real number. So just R is the set of all the real numbers. Okay, but in the case of an R squared, or it is simply called R2. Okay, so in this case, it can be thought of like R by R. So that is just the notation to represent the two-dimensional real numbers, or two-dimensional vector. Okay, so this is this is the set of all the possible real valued two-dimensional vectors. Okay, so any vector in two-dimensional case will belong to this R2, and so we use this kind of notation, right? So this is an element of a set, right? So it's just like maybe 3, something like this. Okay, so this is the set that contains this element, right? Okay, any questions so far? Okay, so far so good, right? Okay, then we can define the notion of the equality between the two vectors and the vector sum, or the scalar multiple of a vector, and also the vector product, or the multiplication of a vector. Okay, so we will kind of study those different operations defined using those vectors. Okay, so let's look at this example. So we are given these two-dimensional vector called u and v, and let's just compute for u and like this. Okay, so in this case, for u is so it's in this case 4 times 1 and -2. So scalar times a vector, right? So it is just a element-wise multiplication of that same scalar value, right? It's quite easy, right? And so this is the vector. Okay, and then we can obtain this vector as well. And what about their sum? Yep, we just perform element-wise addition or summation. Okay. Now, when dealing or when considering this vector, we can think of their geometric kind of space. And so you guys know that given a vector of 3, 4, for example, suppose this is u, and then we can imagine like R2 as this plane, right? Two-dimensional plane. So this is an x1 and x2, and so this guy is 3, 4. So this guy is our u, right? So particular vector will correspond to particular point in a two-dimensional space, right? And this vector, is corresponding to a particular point, but also we can think of this vector as this line segment that has a particular direction, right? So this line segment always start from the origin, or over here, right? and then this is another end point of our line segment, right? Okay. And then now we can also think of, for example, yeah, how about 2u and their geometric meaning? So in this case, 2u will be, of course, 6, 8, right? So we know it is 6, 8, which is corresponding to this point, and so the resulting vector is this guy, right? So in terms of this vector shape or something like that, so the vector direction doesn't change, but only the vector length is stretched or shrunken by our scaling factor, right? Okay, what about the vector addition? Okay, I mean, although they look quite trivial, I mean, they are really simple, but this kind of geometry kind of sense, or their relationships, or their corresponding operations is really, really important when studying linear algebra throughout our class. So even though this look quite simple, but yeah, please keep that in mind. Okay, so in the case of vector addition, okay, we know that the vector addition of these two will be corresponding to this point. And how do we obtain this point? And then we first draw this parallelogram, right? Parallelogram. So you guys know that this line, these two lines, those two lines are parallel and having the same direction and the same length of the vector, right? So also these two lines will also have the same length and the same direction, right? And so we obtained we drew this parallelogram, and then we can think of this opposite point, diagonally opposite point from the origin. So this guy, or this vector, this vector is the sum of this u and v. Okay, so what about this guy? For example, 2u plus 3v, and in this case, we first scale them by their respective scalar multiple. So we have 2u over here, and 3v is somewhere around here. So 1, 2, 3, right? 1, 2. Okay. Okay, you can imagine the opposite point, right? Okay. We can extend this two-dimensional vector into much higher dimensions, including three-dimensional vector or n-dimensional vector, right? But up to three-dimensional point, we can draw these points in two-dimensional or three-dimensional kind of a space, right? But beyond that, or four or more dimensional vectors, we cannot think of their geometric kind of positions and things like that. But all the operations will be essentially the same. Okay, so they are all analogous to what we can understand in the 2D or the 3D cases. Okay, and then bunch of these relations about their vector arithmetic, involving this summation or scalar multiple and so on, right? And here, I keep forgetting to fix this slide, but there is a kind of really small error in this slide. That error is this guy. So my question about it is are these zeros a vector or scalar? So the answer is these are vector. Okay, so for example, suppose we have 3, 4, so two-dimensional vector, and plus 0. So is this operation defined? It is not. Okay, because their dimension doesn't match. So we can, of course, perform this scalar multiple. Okay, we defined this operation, right? But in terms of an addition, yeah, we need to satisfy that these elements that participate in this addition should always have the same dimensions. Okay, so in this case, even if we want to add 0 vectors, I mean zeros with the vector, and that 0 should be also a vector like this. Okay, so in that sense, this 0 is violating our notation rule. So this 0 should be like boldface 0. Are these boldface already? I'm not sure, but at least we know that these should be a vector version of 0, which should be denoted as a boldface. Okay. Okay, and then this minus mu or negative u is the same as negative 1 times vector u, right? And then in this case, yeah, we know this scalar multiple is corresponding to like a stretching the vector by that scaling vector. But what if we just scale this vector by negative 1? Okay, in this case, yeah, the vector direction will be like this, right? So the same length, but now the direction is reversed, right, or opposite. So that is the meaning of multiplying with the negative scalar. Any questions? Okay. Yeah, I think it is quite easy so far. And now we study the new notion of this linear combination. Okay, linear combination. So linear combination, I mean, I think you guys are somewhat familiar with this notion of linear combination to some degree. So this is the formal definition of a linear combination. So suppose we are given these ingredients or our base elements, which are all vectors. Okay, so v1 through vp's are all vectors, and now we have a p different vectors, right? But they are all living in or belonging to the same dimensional space of Rn. Okay, so this is an initial or problem setting. Okay, and then we can think of this guy. So first, for each vectors, we perform the scalar multiple. Okay, and then just add them together. That's it. So that is called a linear combination of the given vectors. And also, let's also note that this C1 through CP is represented as a plain or non-boldface letters, right? And so that indicates they are scalars. Okay, so I think still it is quite easy. But now it's time to relate this with our linear system that we studied in the previous chapter. Okay, so now let's think of this kind of example where we are given these 2 vectors, okay, and also another vector b. And then now the question is, is it possible to obtain b, or is it possible to write this vector b as a linear combination of a1 and a2? It can be any linear combination of a1 and a2. Okay. In other words, we can c1 and c2 and plus. That is a linear combination, right? So can we represent the same vector b as a linear combination of these 2 given vectors? Okay. And if we can find, if it is possible, and then what is the actual value of c1 and c2? So that is the question. Okay, and then now we can formulate, or we can write this as the following equation. So instead of using the coefficient as c1 and c2, let's use just different notation as x1 and x2, right? So here, even though it looks quite simple, and then we have to be careful about their size, because we sometimes deal with a vector or matrix or scalar. So all of them may have a different size. So in this case, so these are scalar, right? And this A1 and A2 are vector in Rn. And for example, if they are in three-dimensional space, and then we have these three-dimensional vectors, and also and B is also a three-dimensional vector. And here, I don't think this is a boldface, so this is also an error, right? I need to take a note because I keep using this faulty slide for 5 years. But anyways, they have to be in a boldface. Okay, so you can now understand this equation, right? So in this case, it's a 7, 4, -3, which is this guy, and this guy is 1 and -2 and -5, right? And 2, 5, 6. Okay. Okay, so now we can at least understand this equation, and our task is to find the solution for this x1 and x2. Okay, and sometimes it may not be it may be impossible at all to find any particular x1 and x2. Okay, so we will study these issues in more detail. But now let's just mechanically rewrite this equation, okay, without too much of our spirit or intuition. So x1 times this, x2 times this is equal to this, right? And then we can apply this a scalar multiple, right? So x1 times 1 and -2 times x1 and so on, right? So we can write this equation into here. Okay, and then we can add those two parts of a vector over here into one. That vector is represented in this form, right? Even though it's a little bit fat, but this guy is a single scalar value, right? This guy is another scalar. Okay, that scalar. So what is the meaning of this vector is equal to this vector? So we haven't explicitly defined the equality between the vector yet, but it is quite obvious. So for example, 1, 2, 5 is equal to 1, 2, 5. That is quite true, right? But what about this guy? 1, 2, 5 and 1, 3, 5. Is it equal or not? It is not, right? So the definition of equality between the two vectors is that every element in the corresponding dimension should be the same, right? So by applying this notion, this really simple notion, given this equality between the left and the right hand side of our vectors, and then we can rewrite it into this form. The first element should be the same as 7, the second element should be the same as 4, and so on, right? And so we suddenly obtained linear system, right? So again, we started from this kind of new problem, right? So the problem was given two vectors, and then we imagine there some linear combination of them, and then we want to make that linear combination is the same as the given vector b, right? So this kind of problem is the same as solving this linear system, okay? But we have to think of their physical meaning a little bit more. So in this case, our variable to solve or determine is just a variable of x1 and x2, right? Because they were just initially given variables where we have to solve our linear system, right? But what was their role? Okay, what was their role in the initial setting over here? So in this case, that solution or the solution for our variable, or what's the role of these variables? The variable is actually the scalar multiple of each vector that we are given. So overall, we want to obtain this linear combination, right? And then in order to obtain this linear combination, we want to determine this scalar multiple of each vector in a way that their sum, okay, their sum is equal to a given vector. Okay. And then the rest of the story, or how to actually solve this kind, this, by the way, this is called a vector equation because we are simply given a equation where these vectors on the left and the right hand side should be the same. So it is simply called a vector equation. Okay, so we can think of it as a vector equation version of a given linear system. So we have a linear system, and then we have its corresponding vector equation version. Okay, so they are they are essentially the same. Okay, but our linear system can be represented in the form of this vector equation. Okay, so how to solve this vector equation? In other words, how to obtain this x1 and x2 as a scalar multiple of this linear equation, linear combination, to be the same as the given vector is actually by following the Gaussian elimination. The actual solving process is it hasn't changed. So once we obtained how to solve it, we perform Gaussian elimination, and then this is our reduced echelon form, right? And then here, fortunately, we have two vectors. So two variables, and then two variables, but the three equations. But fortunately, we didn't have any pivots over here, right? So because we don't have a pivot on the last column, we know that this has a solution. And does it have a unique or infinitely many solution? Let's check whether we have a free variable or not, right? So we have a two variable, but every column has a pivot. So we have unique solution. And what is the unique solution? 2 and 3. So x2 being 2, x1 is equal to 3, right? Okay, so the actual process of obtaining the solution is just the same of applying the Gaussian elimination. Let's see. But let's think of their meaning. Okay, so suppose the final solution of this vector equation was obtained as x1 is equal to 3, x2 is equal to 2. Okay, so let's think about their meaning or physical meaning of these actual solution by using this vector equation. Okay, so in this case, we obtained over here 3 and 2. Okay, so if we think of this problem, and then we can we can consider this problem as follows. So to just simplify the problem, let me just remove the third entry so that we can think of it in a two-dimensional space. Okay, and then in this case, it is this guy, right? But still, the solution will remain the same, right? But anyways, so in this case, we are initially given 1, -2. So in this case, it's 1, -2 over here. So this vector is a1, and a2 is 2, 5. So this is an a2. Okay, and then now what is b? B is 7, 4. 7, 4 over here. So this is our b, right? So we are initially given a1 and a2, And then what is their physical meaning of linear combination? So from this example, so I already explained their geometric interpretation of this linear combination, where we, for example, used 2 and 3 as a scalar multiple, right? So given an initial 2 vectors, we first stretch, right? Extend their lengths by that scalar multiple, and if it is a negative value, and then we reverse the direction, and then also stretch by that absolute value, right? Okay, and then once we stretch it, each respective vectors, and then it's time to form our parallelogram. And then for that, the fourth or the last vertex of our parallelogram is our result, or the final output of this linear combination, right? So if we think of this kind of physical or geometric interpretation of this linear combination of the vectors, okay, and then let's go back to this problem. So again, we want to find the linear combination of an A1 and A2, which is the same as B, right? So in this case, we want to find our parallelogram, okay, where the fourth vertex of this parallelogram is exactly coinciding with our B. So how can we draw this parallelogram? So let me draw that. Okay, so let me do some. Great. Yeah. Okay, so in this case, let me try my best, but let's see. So we want to have this as a fourth point of our parallelogram, and let's see. I need a little bit more. Okay. Okay. Okay, so roughly I created the parallelogram, right, where the first and the second, third, and the fourth point is coinciding or the same as the given vector B. Okay, so in this case, our problem or our goal is to determine those value, which is a respective scalar multiple of each vector, to form this parallelogram, right? So in this case, if we obtain this parallelogram, and then so given this A2 over here having this length, and that should be stretched by that amount, right? So it seems for example, like a 1.5 right, because the length of it seem to have this kind of ratio, but I may have drawn kind of a little bit wrongly, but actually if we draw this really nicely, and then this ratio should be 2, because this 2 is actually the solution that we obtained over here. So what I'm trying to point out or emphasize is, what is the physical meaning in this geometric kind of coordinate system for this solution that we obtained through our Gaussian elimination. So that is corresponding to this the optimal or the exact ratio of each vector to extend so that we match or coincide this point with the given vector B. And in this case, it seems to be, yeah, in this figure, it seems to be like 1.8 times the original vector, but this is actually 3, okay? Because it is 3. So yeah, that is because like it says 2, right? So this doesn't seem to be 7, right? So that's why this kind of distortion, yeah, is plain over here. But yeah, you get the idea, right? Okay, then in the remaining time, let me explain what I think is the most important part. So, how can we think of this geometric interpretation of the case where we have no solution at all? So, yeah, let me just directly give an example. Yeah, let's think of like 3-dimensional space. Okay, so 3-dimensional space, and then now we are given only the 2 vectors. Yeah, so again, in a 3-dimensional space, we are given just 2 vectors. For example, 1, 2, 3, and 2, 3, 4. Okay, having a particular direction and particular length. Okay, and then suppose our vector b. Okay, vector b is somewhere, yes, somewhere over here. Okay, so again, so we are given this x, y, z axis, and yeah, around here is our origin. And now these 2 vectors are initially given a1 and a2, okay, and then still here this is an origin, and now we are given a vector b over here. Okay, so in this case, do you think the solution exists? Solution doesn't exist because, yeah, what will be the linear combination of these 2 vectors? Okay, so now, yeah, I already explained, or we saw these operations. Given a particular linear combination of whether like a 3 times this vector and 2 times this vector, and then we stretch 3 times this vector and the length of the second vector by 2 times, and then obtain the parallelogram. And then what will be the resulting point? It will be somewhere around here, right? Or let's use some other linear combination. 1 times this vector and 4 times this vector, and then we will only stretch this by 4 times, and then we will obtain a little bit long parallelogram, but we can think of some other point over here, right? So in this case, yeah, even before thinking of our b, we can actually think of all the possible points or the resulting points of this linear combination. So for example, in this 3-dimensional example, we are given this a and a1 and a2, or u and v, and then this plane, so this blue colored plane is the set of all the points of these all the possible linear combination of these 2 vectors. Okay, so for example, this point is in this case, what is the corresponding linear combination coefficient? It will be 1 and 1. What about over here? It is like 3 times u and 1 times v, right? So this vector. Okay, so collecting all these ending points, the collection of these ending points will form this straight plane, right? So in this case, what if our b is somewhere over here? It is impossible to represent that vector b as a linear combination of this u and v. Okay, so this is when we have no solution at all. Okay, so okay, so let me spend just 1 more minute. Okay, so here there is a really important notion that you have to be really familiar with. So this blue plane, okay, is called span of u and v. So what is the mathematical definition of this span? Given a set of vectors, we consider all the possible linear combinations. where we can consider this, or we can consider this, or we can consider this, or any other real values. Okay, so collecting all these points and forming a set of these points, that is called a span. So if a given vector B is belonging to our span, that's when we have a solution. Or if B is not in this span of U and B, and then that's when we have no solution at all. Okay. Okay, so this is a really, really important concept. So yeah. But we will continue next Monday. And you guys received the email, right? So the first homework was posted, so it's due next Tuesday, I think. Okay. And also we opened some KakaoTalk chat rooms, so where you can just post your questions and so on. Okay, that's it. Thanks. 네.
아까 세 개 원래 X, Y, G잖아요.
네.
근데 그 마지막 거 그냥 왜 없애신?
아, 그거요? 아, 그러니까 그냥 그거를 나타내려면
G까지 그려야 돼.
그게 이제 3차원, 네, 맞아요. 3차원에서 그리기가 번거로우니까 그랬던 거고요.
그냥 2차로 예로
네, 맞아요. 예로만
그냥 지운 거죠?
네, 그냥 지운 거예요. 그냥 임시로 지운 거예요. 맞아요.
저 좀 안 와닿는 게 원래 벡터라는 게
네.
이제 방향성과 어떤 길이를 가진
네.
개체로 이해하고 있었는데
네.
거기서 이제
네.
이게 보면 이제 우리가 이 컬럼 벡터로부터 어떤 지오메트릭 포인트를
네.
정의를 할 수 있다는 게 근데 중요한 거는 이 벡터는 이 점에 대한 정보를 주는 게 아니라 그냥 이 방향성에 대한 의미만
네. 그러니까 벡터라는 게 원래 우리가 방향과 크기를 가지는
네.
애라고 얘기하잖아요.
네네.
근데 이제 우리는 그 벡터가 시작하는 시작점을 언제나 원점으로 고정을 시킨다라고 가정하면
네.
그러면 그 방향과 어떤 특정한 방향과 특정한 크기를 가진 어떤 그 선으로서 나타내는 벡터가
그 어떤 점을 지정하게
그렇죠. 항상 그러니까 스타팅 포인트는 원점이라고 생각을 한다면 그 선과 그 방향을 가지는 그 정보는 어찌 됐건 그 이제 그 공간상에서의 그 끝점으로 이렇게 동등하게 이제 나타내어질 수가 있다는 거죠.
그러면 결국에는 벡터는 이제 점을 정의해주는 방법이다라고
네.
볼수 있는.
벡터 이꼴 점이라고 생각할 수 있어요. 네.
그리고 또 궁금한 게 그냥 너무 똑같아 보여서 그런데 linear combination이라는 단어랑
네.
vector equation이라는 거에 결국엔 같은 단어로
네.
볼 수.
그 리니어 이퀘이션은 그 자체로서는 이꼴 사인은 없죠. 그러니까 이제 3u 플러스 2v 이거가 리니어
그건-
컨비네이션인 거예요.
근데 는
선형처럼.
사인이 있잖아요.
그러니까 는 사인은 그 이퀘이션 말 그대로 이제 방정식이 그러니까 여기 방정식이 실제로 뭔가 주어지거나 그 방정식 고려를 할 때 그 이퀘이션이 되는 거고요.
네.
이 레프트 핸드 사이드
없어도
파트만
이것만
그렇죠.
해도 linear
저것만
combination이
이제
되는
선형
거고.
결합이라고 우리가 부르는
뭐 이게 는 뭐 어떤 equation 생기면 그때는 이제
거예요. 그걸 이퀘이션이라고 하고.
그냥
네.
하나 더 있는 차이.
네, 맞아요. 네. 네.
알겠습니다.
감사합니다.
네.
그 숙제가 이렇게 나와 있으면
네, 네.
저희가 1.3
챕터를 그거에 이제 엑셀사이즈 5, 9, 10, 7,
1.4는 안 해요.
1.4는
아직.
네, 맞아요. 그게
네.
제가 조금 일찍 나오긴 했는데
네.
1.4를 이제 우리가 월요일에 배울 거네요.
그럼 월요일 날 배워서 다음
좀
날까지.
짧을 수도 있겠네요. 네, 그러면 그걸 조금 더 고려를 한번 해볼게요. 네, 진도를 좀 더 빨리 나갈 계획이었는데 좀 그렇게 됐네.
이 말이
네.
이게 벡터 공간인데.
네.
벡터 공간이
n 차원의 벡터 공간을 의미하는 단어
그럼-
노테이션이에요. 이게.
n 차원의 벡터 공간은
네.
그 n 개의 벡터, 그러니까 n 차원이고
네.
n 개의 벡터의 선형 결합으로 나타내죠. 아니.
자, 이게 만약에 n이 만약에 3차원이고 3이고 p가 만약에 5예요.
네.
그러면 일단은 v1부터 v5까지의
네.
5개의 벡터가
네.
다 3차원의 벡터란 뜻이고요.
네.
그렇죠? 그러면 5개에 대한 리니어 컨비네이션은 그 5개의 첫 번째는 그 코에피션트를 2를 곱하고 두 번째는 뭐 5를 곱하고 세 번째는 뭐 마이너스 1을 곱하고
네.
각 그 5개마다 우리가 곱해주는 상수값들
네.
그 다음에 그걸 다 합치는 거죠.
그러면 최소 n 차원이면 최소 n 개인 거예요. 필요한
그러니까 그게 이제 그 벡터들이 지금 몇 차원에 살고 있는 벡터들을 우리가 다루느냐와
예.
그래서 아까 거기 n이라는 값과
예.
네, 그 다음에 그 벡터 우리한테 주어지는 그 벡터의 개수 있잖아요.
네.
그 두 가지 요소가 다 중요하고요. 실제로 우리가 그러니까 3차원에서 벡터가 하나만 심지어 하나만 주어질 수 있고